All right, let's talk about electricity, but in a totally different way. We're going to step away from thinking about forces, all the pushes and the pulls, and we're going to enter this much cleaner world of energy. We're going to explore something called electric potential, which is basically a way to map out the invisible energy landscape that charges create all around them.
Look, if you've ever tried adding up a bunch of electric force vectors, you know it can be a real headache. You're juggling magnitude, direction, x components, y components. It's just a mess. But what if there was a better way? What if we could just ditch all those arrows and work with simple numbers instead? Well, that's exactly the promise of looking at things from an energy perspective.
And that's our jumping off point. First up, we're going to dig into why physicists even bothered to make this shift. Trading the headache of vector forces for the beautiful simplicity of scalar energy. So the whole reason we can even do this is because the electric force is what we call conservative. Now, that's a huge deal in physics. It means we can directly connect it to potential energy. And the rule, as you can see, is pretty straightforward. The change in a system's potential energy is just the negative of the work done by the electric field. So think about it. When the field does positive work, like gravity pulling an apple towards the ground, the potential energy of the system actually decreases. Okay, but there's a little problem here. Potential energy is great, but it depends on the charge of the particle you're actually moving. A bigger charge is going to have more potential energy in the exact same spot. This makes it a property of the whole system, not a property of the electric field itself. What we really want is a way to describe the energy landscape of the space, no matter what we decide to put in it.
And that brings us to the real star of the show today, electric potential. This is the concept that lets us really talk about the energy of the field, making it a true property of the space itself.
And the solution is it's beautiful. It's so simple. We just define electric potential, which we call V, as the potential energy per unit of charge. We just divide out the charge Q. And by doing that, we've created something new that doesn't care about the test charge anymore. It's now a property of a single point in space. We measure it in joules per coulomb, which we give a special name, a volt. Yeah, that's the same volt you see on all your batteries.
So, how are you supposed to visualize this invisible property of space? Well, the absolute best way to get your head around it is to think of a topographical map, the kind a hiker would use. Electric potential creates an unseen energy landscape, complete with hills, valleys, and flat spots that charges have to navigate. So, if potential is a map, how do we actually draw it? Let's take a look at how you can actually visualize this electric landscape.
Take a look at this map right here. The gold lines, those are what we call equipotential surfaces. They are exactly like the contour lines on a hiking map. Every single point along one of those gold lines is at the same electric height, the same potential. And the purple lines? Those are the electric field lines we already know. Notice how they always point from high potential to low potential? They show you the path a positive charge would naturally roll down. And here's the kicker. They always cross the equipotential lines at a perfect right angle. This map analogy just keeps getting better. If you're out hiking and you walk perfectly along a contour line on a hill, you aren't going up or down, right? It's exactly the same for a charge. If you move a charge along an equipotential path, it costs zero energy. No work is done. That's because the electric force is always pushing perpendicular to the way you're going, so it can't give you a push or a pull along your path. It's kind of like a free ride across the landscape. And if we want to get mathematical, the landscape created by just one single point charge is described by this really simple formula. The potential V only depends on the charge Q that's making the field and how far away you are, R. So a positive charge gives you a positive potential, that's our energy hill, while a negative charge gives you a negative potential, creating an energy well or a valley that positive charges will just fall right into. Now, it is absolutely crucial to keep these two ideas separate. Think of it like this. Potential is a scalar. It's like temperature. It's just a number. Every point in space has a single value. The electric field, on the other hand, is a vector. It's like wind. It has a strength and a direction at every point. And that's the magic here. Potential lets us work with simple numbers instead of wrestling with all those complicated vectors. Okay, so what about going the other way? If we have this beautiful potential map, can we figure out the electric field, the actual force a charge would feel? The answer is a definite yes. So look at this diagram. When we move a little test charge from one equal potential line to another, the work that gets done depends on the electric field. But more specifically, it depends on the part of the electric field that's pointing along the same direction as our path. This right here is the link. This is how we connect the potential map back to the field vectors.
And it all boils down to this really intuitive idea. The electric field is just the steepness of the potential landscape. The fancy term is the negative gradient, but really, just think of it as the slope of the hill. The field always points in the direction of the steepest descent, straight downhill. So if you look at your potential map and see the contour lines all bunched up really close together, that's where the hill is steepest, and that's where the electric field is the strongest. Okay, so this is all great theory, but where does it actually show up in the real world? Let's look at a really powerful and frankly life-saving application that involves conductors and lightning. All right, quick review on the properties of a conductor that's just sitting there in equilibrium. First, any extra charge you put on it, it immediately runs to the outer surface. Because of that, the electric field inside the conductor is always zero. And if the field inside is zero, well then it takes zero work to move a charge from one point to another inside. And that means the entire conductor, every point on the surface, every point on the inside, is one big equipotential surface. It's all at the same potential.
And this leads us right to a classic question. We've all been told that you're safe inside a car during a thunderstorm. But why? Why exactly? Let me give you a hint. It has nothing to do with the rubber tires. The real answer is all about the electric potential we've just been talking about.
See, the car's metal frame is an amazing conductor. When lightning strikes, bam, a massive amount of charge gets dumped onto that frame. That charge, following the rules, instantly spreads itself out all over the outer surface of the car. And in that moment, the entire car body becomes a single equipotential surface. Sure, it's at a crazy high potential, maybe millions of volts, but the key is that it's the same potential everywhere on the car. And that is the one thing that saves you. Current flows because of a potential difference, a voltage. But you're sitting inside this perfect equipotential shell. The potential at your head is exactly the same as the potential at your feet. And if there's no potential difference across your body, no current can flow through you. You're completely unharmed while millions of volts are raging just outside the metal frame. This idea of potential as an energy landscape is honestly one of the most powerful concepts in all of physics. It takes these really complex force problems and turns them into simple questions about altitude and terrain. It really makes you wonder, doesn't it? If electric potential helps us see this invisible landscape for electricity, what other fundamental forces have their own invisible terrains, shaping all the interactions that govern our entire universe?